The Toyota assembly line had been silent for 3 weeks, costing $2 million per day. 20 engineers had failed to solve the robotic welding crisis. When Dr. Sarah Chen walked into the Georgetown plant carrying her oversized toolbox, the veteran mechanics just smirked. They had no idea what was coming. The Georgetown Toyota manufacturing plant stretched across 300 acres of Kentucky farmland, normally humming with the synchronized precision of automotive production. But on this humid July morning in 2019, the main assembly line stood eerily quiet. The massive robotic welding stations that should have been sparking with automated precision were frozen in place, their mechanical arms suspended like sleeping giants. The silence was deafening and expensive, $2 million per day in lost production, with ripple effects threatening the entire North American supply chain. 20 engineers clustered around the malfunctioning robotic welding system, their faces etched with 3 weeks of mounting frustration and sleepless nights. Laptops, diagnostic equipment, and replacement parts littered the factory floor like the remnants of a technological battlefield. Jim Morrison, the 58-year-old team leader, wiped grease from his weathered hands as he surveyed the chaos. With 30 years of hands-on experience from apprentice mechanic to senior engineering supervisor, Morrison had seen every possible mechanical failure. His reputation was built on solving the unsolvable, but this crisis was testing even his legendary troubleshooting skills. "We've replaced every major component twice," Morrison muttered to his deputy, Mike Rodriguez. "New servo motors, updated software, recalibrated sensors. The diagnostics show everything's perfect, but the damn thing won't hold position." The team had worked around the clock, bringing in specialists from Detroit, consulting with Toyota's engineers in Japan, and even flying in the original German manufacturers of the robotic systems. Each expert had left shaking their head, adding to the growing pile of failed solutions and mounting corporate pressure. The factory floor's tension was broken by the soft squeak of wheels rolling across polished concrete. Dr. Sarah Chen entered the cavernous space, pulling a worn toolbox that seemed almost comically oversized for her petite 5'2" frame. Her thick-rimmed glasses reflected the harsh industrial lighting as she surveyed the scene with quiet intensity. At 32, Sarah looked even younger, in her oversized lab coat, her appearance drawing skeptical glances from the assembled engineers. Despite her MIT Ph.D. in mechanical engineering and 8 years of specialized experience in industrial robotics, she still faced the same dismissive attitudes that had followed her throughout her career. Morrison's expression shifted from desperate hope to barely concealed irritation as he watched Sarah approach the disabled robotic system. The corporate executives had insisted on bringing in fresh perspectives, but Morrison saw only another academic theorist who had never gotten her hands dirty with real machinery. "Great," Morrison muttered under his breath to Rodriguez. "Now they're sending us grad students. What's next? A high school science fair winner?" Sarah overheard the comment, but showed no reaction, her focus entirely on the massive robotic welding station. She moved with deliberate precision, her trained eye cataloging details that others might miss. "Dr. Chen," Morrison said with forced politeness, "we've been through every possible diagnostic. The system's been completely rebuilt from the ground up. Unless you've got some magic MIT theory we haven't tried, I'm not sure what you think you can add here." The other engineers exchanged glances, some smirking at Morrison's thinly veiled skepticism. They had all heard about the diversity hire from corporate headquarters, another box-checking exercise that would waste time they didn't have while the production losses mounted. Sarah said nothing in response to Morrison's challenge. Instead, she pulled out a worn notebook and began what appeared to be a methodical observation of the robotic system. For 2 hours, she moved around the machinery like a detective, studying a crime scene, occasionally jotting notes, but never speaking. The other engineers continued their work, replacing components and running diagnostics while casting occasional glances at the quiet woman who seemed to be doing nothing productive. Some whispered jokes about academic types who thought they could solve real-world problems by taking notes. But Sarah was listening to something the others had missed. Every 47 seconds, she heard a subtle vibration, barely perceptible but consistent. It wasn't in any of the diagnostic reports, wasn't flagged by the sophisticated monitoring systems, but it was there. "What exactly are you doing?" Rodriguez finally asked his patience wearing thin as he watched Sarah kneel beside what appeared to be a minor support structure. Sarah looked up from her examination of a seemingly insignificant mounting bolt. "Learning," she said, simply returning to her inspection with the same methodical intensity, while the other engineers focused on the complex electronic systems, servo motors, and sophisticated software that controlled the robotic welders. Sarah's attention was drawn to something far more basic, a single mounting bolt at the base of the primary robotic arm. The bolt appeared secure to casual inspection, but Sarah's trained eye detected something the others had missed. Using a precision measuring tool from her kit, she discovered that the bolt had loosened just enough to create a microscopic misalignment, 0.3 millimeters of play that was invisible to standard diagnostics, but catastrophic to the system's precision requirements. "Found it," Sarah announced quietly, her voice cutting through the ambient noise of the factory floor. Morrison looked up from a computer terminal, where he was running yet another software diagnostic. "Found what?" Sarah pointed to the seemingly insignificant bolt. "Your problem. This mounting point has worked loose. It's creating a positional error that cascades through the entire welding sequence." The veteran engineer's expression shifted from skepticism to disbelief. "That little bolt, we checked all the major mounting points weeks ago. There's no way something that small could shut down the entire line." Sarah stood up, her notebook filled with precise measurements and calculations that told the story of the system's failure. The robotic arm requires positional accuracy within 0.1 millimeters for proper welding. She explained, her voice gaining confidence as she moved into her area of expertise. "This bolt has loosened enough to create 0.3 millimeters of play in the mounting system. Every time the robot moves to a new position, that tiny amount of flex compounds through the mechanical linkages. By the time it reaches the welding head, you're looking at positional errors of several millimeters." Morrison frowned, still skeptical. "But the diagnostics would catch that kind of error. The system's supposed to self-correct for minor variations." "The self-correction algorithms assume the mounting points are rigid." Sarah continued, pulling out her laptop to show a simulation she had been running. "When you have this kind of microflex, the correction systems actually make the problem worse. They're trying to compensate for what they think is a sensor error, but they're actually fighting against mechanical instability." The other engineers began gathering around as Sarah's explanation revealed the elegant simplicity of a problem that had confounded them for weeks. Despite Sarah's clear explanation, Several team members remained unconvinced that such a simple mechanical issue could have caused their sophisticated system to fail so completely. "Look, Dr. Chen," said Tom Bradley, a senior systems engineer with 15 years of experience, "we appreciate the theory, but we've been through every mechanical component. If it was just a loose bolt, we would have found it weeks ago." Rodriguez nodded in agreement. "Plus, even if that bolt was loose, the system should still function. These robots are designed with tolerances that account for minor mechanical variations." Morrison crossed his arms, his skepticism evident. "I've been working on industrial machinery since before you were born, and I've never seen a single loose bolt shut down an entire production line. The computer systems are too sophisticated for that." Sarah listened to their objections without defensiveness, understanding that her youth and appearance made it difficult for the veteran engineers to accept that she might have found something they had missed. But she also knew that her analysis was correct, and she was prepared to prove it. "I understand your skepticism," she said calmly. "Would you like me to demonstrate?" Sarah asked Morrison to run the robotic system through a standard welding sequence while she monitored the problematic mounting point with her precision measuring equipment. As the robot moved through its programmed motions, her instruments clearly showed the microscopic movement that was invisible to the naked eye. "Watch this," Sarah said, pointing to her laptop screen, where she was displaying real-time measurements. Every time the robot extends to full reach, the mounting point flexes by exactly 0.3 millimeters. The system tries to compensate, but the flex is inconsistent because it depends on the robot's position and load. The data was undeniable. The sophisticated diagnostic systems had been looking for electronic failures, software bugs, and major mechanical problems, but they weren't designed to detect this kind of subtle structural issue. "Son of a bitch," Morrison muttered as he watched the measurements fluctuate in perfect correlation with the robot's movements. "You're right. But how the hell did we miss something so basic?" Sarah's response was diplomatic, but pointed. "Sometimes the most obvious problems are the hardest to see, especially when you're looking for complex solutions. Fixing the immediate problem would have been simple. Just tightening the loose bolt would restore the system's rigidity. But Sarah saw an opportunity to do more than just repair the existing design. She could improve it. "We can fix this in 20 minutes, she told Morrison, "but I'd like to suggest some modifications that will prevent this from happening again and actually improve the system's overall performance." Using her laptop, Sarah showed the team a redesign of the mounting system that would not only eliminate the possibility of similar failures, but would actually increase the robot's precision by 23% over the original specifications. The current design relies on static mounting points that are vulnerable to loosening over time, she explained. "If we add dynamic dampening elements here and here, we can absorb vibrations that cause the loosening while also improving positional stability." The modifications would require some additional components and about 2 hours of installation time, but the long-term benefits were significant. Morrison found himself impressed not just by Sarah's diagnostic skills, but by her ability to turn a repair into an upgrade. "Do it," he said, his earlier skepticism replaced by genuine respect. As word spread through the plant that a potential solution had been identified, the pressure on Sarah intensified dramatically. Corporate executives, plant managers, and Union representatives gathered around the robotic welding station, all desperate for the production line to resume operation. Dr. Chen had said, plant manager Robert Hayes, a man whose career depended on keeping the Georgetown facility profitable, I need to know with absolute certainty that this will work. We can't afford another failed attempt. Every hour of downtime is costing us $83,000. The weight of expectation was palpable. 20 experienced engineers had failed to solve this problem over 3 weeks, and now a young woman with a theory about a loose bolt was claiming she could not only fix it, but improve it. The skepticism in the room was thick enough to cut with a knife. Morrison, despite his growing respect for Sarah's analysis, felt compelled to voice the concerns that everyone was thinking. Dr. Chen, I want to believe you're right, but if this doesn't work, we're looking at potentially another week of downtime while we undo whatever changes you make. Sarah understood the stakes. Her reputation, her career, and the livelihoods of thousands of workers hung in the balance. But she also knew her analysis was correct, and she had the confidence that came from years of rigorous training and hands-on experience. Sarah began her work with the methodical precision that had characterized her entire approach to the problem. First, she tightened the loose mounting bolt, immediately eliminating the 0.3 mm flex that had been causing the positional errors. The watching engineers held their breath as Morrison initiated a test sequence. For the first time in 3 weeks, the robotic welding arm moved through its full range of motion without triggering error codes. The precision measurements showed perfect positional accuracy. "Holy shit," whispered Rodriguez, "it's actually working." But Sarah wasn't finished. Working with practiced efficiency, she began installing the dampening modifications she had designed. Each component was precisely positioned and calibrated, transforming the simple repair into a comprehensive system upgrade. The modifications required her to crawl into tight spaces around the massive robotic system, her small stature proving advantageous as she accessed mounting points that would have been difficult for larger engineers to reach. Her movements were confident and precise, demonstrating the kind of hands-on expertise that belied her academic background. "Where did you learn to work like that?" asked Bradley, watching Sarah install a complex dampening assembly with the skill of a master technician. "MIT's robotics lab wasn't just theory," Sarah replied without looking up from her work. "We built everything from scratch. You can't understand how machines work unless you can build them yourself." After 2 hours of intensive work, Sarah stepped back from the robotic system and nodded to Morrison. "It's ready for full testing." The entire group gathered around the control station as Morrison initiated a complete welding sequence, the same test that had been failing for 3 weeks. The robotic arm moved with fluid precision, each motion perfectly controlled and accurate. But the real test came when Morrison pushed the system to its operational limits, running it through the most demanding sequences in its programming. Not only did the robot perform flawlessly, but the precision measurements showed accuracy levels that exceeded the original specifications by exactly 23%, just as Sarah had predicted. "Unbelievable," Hayes muttered, watching the performance data scroll across his screen. "This is better than when the system was brand new." The room erupted in cheers and applause as the implications sank in. The production line could resume immediately, saving the company millions in lost revenue. But more than that, Sarah's modifications had actually improved the system's performance, potentially increasing production efficiency for years to come. Morrison approached Sarah with a mixture of admiration and embarrassment. Dr. Chen, I owe you an apology. I let my assumptions cloud my judgment, and I'm sorry for that. Sarah's response was gracious and professional. We all bring different perspectives to problem solving. The important thing is that we solved it together. The moment Morrison gave the signal to restart full production, the Georgetown plant came alive with a symphony of mechanical precision that had been silent for 3 weeks. The robotic welding stations resumed their choreographed dance sparks, flying as metal was joined with computer-controlled accuracy. Within the first hour, the production line was operating at 105% of its normal efficiency thanks to Sarah's modifications. The improved dampening system not only eliminated the vibration issues that had caused the original failure, but also reduced wear on other components throughout the system. I've never seen the line run this smoothly, admitted Rodriguez, watching the production data stream across multiple monitors. The quality control metrics are off the charts. Plant manager Hayes was already on the phone with corporate headquarters, delivering the news that would save his career and the jobs of thousands of workers. Yes, sir. Full production resumed. Not only that, but we're seeing performance improvements across all metrics. The financial impact was immediate and dramatic. Instead of losing $2 million per day, the plant was now generating $2.3 million in daily revenue while producing higher quality vehicles than ever before. Word of Sarah's achievement spread rapidly through Toyota's global network. The young engineer, who had been dismissed as a diversity hire, was suddenly being hailed as a problem-solving genius who had saved one of the company's most important manufacturing facilities. Corporate executives who had never heard of Dr. Sarah Chen were now asking for detailed reports on her methodology and requesting her involvement in other challenging projects. The solution that had seemed impossibly simple in retrospect was being studied and implemented at Toyota facilities worldwide. Dr. Chen said Hayes during an impromptu celebration in the plant cafeteria, "I've been in manufacturing for 25 years, and I've never seen anything like what you accomplished today. You didn't just fix our problem, you made us better." The transformation in how her colleagues viewed her was immediate and profound. The skeptical glances had been replaced by genuine respect and admiration. Sarah's solution was remarkable, not just for its effectiveness, but for its elegant simplicity. While 20 engineers had focused on complex electronic and software solutions, she had identified a fundamental mechanical issue that had been hiding in plain sight. The dampening system she designed became a case study in engineering schools and was eventually patented by Toyota as a standard improvement for all their robotic welding systems. The 23% improvement in precision translated to measurable improvements in vehicle quality and reduced warranty claims. What impressed me most, Morrison later told a group of engineering students, wasn't just that she found the problem, but how she turned a simple repair into a revolutionary improvement. That's the difference between fixing something and truly understanding it. Sarah's approach demonstrated the importance of combining theoretical knowledge with practical observation, showing that the most sophisticated problems sometimes had surprisingly simple solutions. Sarah's diagnostic approach became known as the Chen method. throughout the automotive industry, a systematic combination of acoustic analysis, precision measurement, and holistic system thinking that challenged traditional troubleshooting protocols. What Dr. Chen did was revolutionary, explained Dr. Michael Torres, a professor of mechanical engineering at Georgia Tech who studied the Georgetown incident. She didn't just solve a problem. She demonstrated a completely different way of thinking about complex system failures. The Chen method emphasized listening to machines as much as analyzing their data, recognizing that sophisticated diagnostic equipment could sometimes miss simple mechanical issues that were obvious to trained human senses. Sarah's ability to hear the 47-second vibration pattern that had been invisible to electronic monitoring became a legendary example of the importance of human intuition in engineering. Manufacturing facilities across multiple industries began incorporating Sarah's methodology into their standard operating procedures. The combination of high-tech diagnostics with old-fashioned mechanical observation proved to be more effective than either approach alone. Training programs were developed to teach engineers how to listen to machinery the way Sarah had, recognizing that the most advanced technology was only as good as the human intelligence that interpreted its results. Sarah's success at Georgetown transformed her from an overlooked junior engineer into one of the most sought-after problem solvers in the automotive industry. Job offers poured in from companies around the world, all eager to hire the woman who had accomplished what 20 experienced engineers could not. But Sarah chose to stay with Toyota, accepting a promotion to senior systems engineer and a mandate to develop new diagnostic protocols for the company's global manufacturing network. Her first assignment was to lead a team of 50 engineers in implementing the Chen method across all North American facilities. "I could have gone anywhere," Sarah later explained, "but Toyota gave me the opportunity to prove myself when others wouldn't. Loyalty matters, and I wanted to help them build on what we started in Georgetown." Her decision to stay demonstrated the same thoughtful approach that had characterized her problem-solving, focusing on long-term impact rather than short-term gain. 5 years after the Georgetown incident, Sarah's modifications and methodology had been implemented in over 200 manufacturing facilities worldwide, saving companies millions of dollars in downtime and improving product quality across multiple industries. The loose bolt that had stumped 20 engineers became a symbol of how the most complex problems sometimes had the simplest solutions, and how fresh perspectives could reveal what experience had overlooked. Sarah's story was taught in engineering schools as an example of the importance of systematic observation, the value of diverse viewpoints, and the power of combining theoretical knowledge with practical application. Dr. Chen showed us that being young and different wasn't a disadvantage. Morrison reflected years later. It was exactly what we needed. Sometimes the outsider sees what the insiders miss. The woman who had been dismissed as a diversity hire had become a legend, proving that competence and insight mattered more than assumptions and stereotypes. For Sarah Chen, the success at Georgetown represented more than just a professional triumph. It was validation of years of perseverance in the face of skepticism and discrimination. The young woman who had been dismissed by colleagues finally received the recognition her skills deserved. "I spent so many years proving myself over and over again," Sarah reflected during a keynote speech at the Society of Women Engineers conference. Georgetown wasn't just about fixing a machine, it was about showing that competence comes in many different forms. The incident became a turning point, not just in her career, but in her confidence. No longer did she feel the need to prove her worth in every interaction. Her reputation now preceded her opening doors that had previously been closed and earning her the respect of colleagues who had once questioned her abilities. Sarah's story inspired countless young women and minorities in engineering, showing them that persistence and excellence could overcome prejudice and preconceptions. The Georgetown incident sparked broader changes in how the automotive industry approached both problem-solving and diversity in engineering teams. Companies began recognizing that diverse perspectives weren't just politically correct hiring practices, they were essential for innovation and problem-solving. The Chen method became standard protocol because it worked, explained Toyota's chief technology officer. But it also taught us that we needed to listen to all our engineers regardless of their background or experience level. Manufacturing companies began implementing fresh eyes protocols, where complex problems were routinely reviewed by engineers from different backgrounds and specialties. The practice of bringing in outsiders to challenge established thinking became a standard part of troubleshooting procedures. Sarah's success also led to increased investment in diversity and inclusion programs, as companies recognized the tangible business value of having varied perspectives on their engineering teams. 10 years later, the Georgetown Toyota plant still displayed a plaque commemorating Sarah's achievement, serving as a reminder that innovation could come from unexpected sources. The Chen method had become so standard that young engineers learned it as part of their basic training, often without knowing its origin story. Sarah herself had gone on to found her own consulting firm, specializing in complex manufacturing problems that traditional approaches couldn't solve. Her client list included companies from around the world, all seeking the fresh perspective that had made her famous. The loose bolt that had stumped 20 engineers had become a symbol of how the simplest solutions were often the most profound.